Let's look at one more example of determining whether a vector is linearly independent or not. So let's check if this v, 110, is linearly dependent on v1 and v2. So v1 is 1, 2, 1, and v2 is minus 2, minus 4, minus 2. So, as usual, this is asking the question, is it possible to write 1, 1, 0 as a linear combination of the other two vectors like this? And we can rewrite this as a matrix equation and then write that matrix equation as an augmented matrix. So that's going to be 1, minus 2, 2, minus 4, 1, minus 2, and augmented with 1, 1, 0. And then do row reduction. And what we get here is this. So we get 1, minus 2, 0, 0, 0, 1, 0, 0, 0. Okay, like this. And because of this second row, this means that there are no solutions. Okay, which means that no, we can't write 1, 1, 0 as a linear combination of these other two. So that might make you think, so is it true that there are no redundancies when we write this span? So, right, when our hope, if we made a good choice for definition of linearly dependent, then it would be the case that this span of these vectors, v1 and 1, 2, 1, v2 is minus 2, minus 4, minus 2, and v, which is 1, 1, 0. So if we made a good choice of linear dependence or independence, then since v is not linearly dependent according to this definition, then there wouldn't be any redundancies when we write down this span. But in fact, there are some redundancies. In fact, maybe you already noticed this middle vector is just minus 2 times the first one. So that means that this span of 3 vectors is actually equal to the span of just the first one, 1, 2, 1, and the last one, 1, 1, 0. So it's true that that v is not a linear combination of v1 and v2, but v2 is actually a linear combination of v1 and v, or even just v1. So somehow this definition that we made about linearly dependence, it doesn't quite capture everything that we would like it to, because it's not really testing, if we have these 3 vectors, it's not really testing if they're all independent from each other. The way that we defined it, this sort of distinguishes one of the vectors and then checks, is that vector a linear combination of the other two? What we'd really like to know is, are any of the vectors linear combinations of all of the others? That's the important question, right? If there's no redundancy at all among any of the vectors, then, every vector hopefully would be required to get the whole span. But this definition isn't quite capturing that. So let's see if we can modify this definition. So what we did is we found, is V a linear combination of the other two, like this? But this definition wasn't quite capturing what we wanted because it privileges V, right? It forces you to choose one vector that's special. Well, you can see that we can ask the same question just by rearranging this equation. So in particular, we could move the v to the right. And in fact, to make it look even less special, let's actually give it a subscript. So it's not special, so let's give it a subscript just like the others. So we can move it to the right. So what we really want to know is 0 equal to a1 times v1 plus a2 times v2 minus v3, and So the question now is, can we solve this equation? So can we solve this vector equation? Well, you can see this still privileges v3 because it's the one that doesn't have a coefficient, and also it's negative. But just by multiplying this entire equation by a new scalar, you get scalars on every vector, and if you want, you can absorb this minus sign into the scalar that's in front of v3. So what happens when you do that is, what you end up asking is it possible to write the 0 vector as a linear combination of these 3 vectors like this? So here's a linear combination of v1, v2, and v3. Is it possible to write 0 as such a linear combination? Well, so on the one hand, this feels like a step in the right direction, because now we aren't treating any of the 3 vectors, v1, v2, or v3, as special in any way, right? We're treating them all equally because they come into this equation in the same way. But on the other hand, we're missing something now, because this equation always has a solution. We could just, for our a's, we could just choose the vector of all zeros, the 0 vector, right? That would be one solution that works, but that's not really saying anything about the vectors v1, v2, and v3 in particular. That's just sort of, that solution exists because this is a homogeneous equation. It's because one side of the equation is 0. So what we're really interested in is, are there any solutions to this equation that other than this solution, right? So the question that we want to know is, are there solutions other than just all zeros? And this solution, since this is the solution of all zeros to a homogeneous equation, remember we call this the trivial solution, because every homogeneous system has this as a solution. So what we're really looking for when we ask, does this equation have solutions, we're really looking for non-trivial solutions. Okay, now if there is a non-trivial solution, then that means that one of these a's isn't 0. So maybe it's I don't know, let's say a sub 2 maybe, right? They can't all be 0, so maybe this is the one that isn't 0. Well, then you can move that term to the other side. That'll leave a1 v1 plus a3 v3 on the right hand side, and then you can divide by a2, and it's safe to do this division because a2 isn't 0. So then you get v2 equals minus a1 over a2 v1 minus a3 over a2 v3. And you see that if there's a non-trivial solution, then some vector, whichever one doesn't have a 0 for a coefficient in this non-trivial solution, some vector is a linear combination of the remaining vectors. So this is sort of pointing us in the direction that, or this is trying to tell us that this new way of thinking about it as non-trivial solutions to this homogeneous equation is a better way of thinking about this linear dependence or independence, because it treats these vectors equally, but it does capture the idea that there's some vector that's redundant. There's some vector that's a linear combination of the others. So for this reason, we will modify our definition of linear independence and linear dependence. So we'll say that vectors v1 through vk are linearly dependent if this equation, the linear combination of them equals 0, has a non-trivial solution. If there is such a solution, then we'll call that a dependence relation. And if the only solution to this equation is the trivial solution, then we will say that these vectors are linearly independent. All right, so just to check our understanding, let's check, is this collection of vectors linearly dependent or independent? If they are dependent, then let's write one as a linear combination of the others. So we want to know if we do, is it possible to take a linear combination of these three vectors and end up with the zero vectors? So a1 times minus 304 plus a2 times 8 minus 1, 7 plus a3 times 2 minus 1, 1. Is it possible to get a non-trivial solution to this equation? Okay, well, we can pile all of this into a matrix as usual. Minus 3, 8, 2, 0, minus 1, 4, 7, 1 times a1, a2, a3. We want to know, are there any non-trivial solutions when this is set equal to 0? So to solve a homogeneous system like this, remember what we can do is take this matrix of coefficients. We don't need to augment because the augmented column is just going to be all zeros as you do your row reduction. So we can just row reduce this and see if the result has, see what the reduced row echelon form of this matrix looks like. When we row reduce this matrix, we get 1, 1, 1. And everything I don't write down is zeros. And remember, what this tells us about this homogeneous system that we wrote down is that the only solution is a1, a2, a3 equals 0, 0, 0. Right? Well, this is the trivial solution. So the only solution to this equation is the trivial solution. Okay, but if the only solution to this equation is the trivial solution, then that's when we call these vectors linearly independent. So these three vectors are linearly independent. There is no dependence relationship between them. As a final example, let's check if these three vectors are linearly dependent or independent. So as usual, we need to just solve the system of equations where these three vectors are our columns times a vector of unknowns equal to 0, right? We need to check, does this have just the trivial solution or does it have other solutions? And to do that, we can row reduce the matrix 4, 20, minus 2, 2, 6, 1, minus 5, minus 26, 3. So row reduce this thing and just see if we get non-trivial solutions or not. So when we row reduce this one, we get (1, 0, minus 11 over 8, 0, 1, 1 over 4, 0, 0, 0. Okay, so this is telling us that A1 has to be 11 over 8 times A3, and A2 has to be negative 1 over 4 A3, and A3 is free. Well, we have a free variable. Since we can choose this variable to be non-zero, that means that there is a non-trivial solution. So we're going to have a non-trivial solution because we have a free variable. And in fact, if you find one non-trivial solution, there will be infinitely many non-trivial solutions because any multiple of, if you have a non-trivial solution, if you multiply all your scalars by some single constant, say c, you get another non-trivial solution. So if there's one non-trivial solution, there are infinitely many. But just to generate some relationships, so they're linearly dependent because there's a non-trivial solution. But to get to write one vector as a linear combination of the others, Right? What we need to do is just write down some non-trivial solution that is a linear dependence relationship between the three vectors, and then solve for one of the vectors. So we can, to get a linear dependence relationship, we can just choose any non-trivial solution. So just make a choice for A3. It could be, I don't know, how about 1? That'll do. So we get A1. So if A3 is 1, that means A1 has to be 11 over 8. So 11 over 8 is A1. So that times our first vector, which is 4, 2, minus 5. Plus, so A3 is 1, so A2 is minus 1 over 4. So minus 1 over 4 times the second vector, 26 minus 26. Plus A3, which is 1, times the third vector, minus 2, 1, 3. And that's equal to the 0 vector, 0, 0, 0. So here's a linear dependence relationship, or a linear dependence relation. And to write one vector as a linear combination of the others, we just need to solve this for one of the vectors. So, low-hanging fruit here, let's solve for that one. So we get minus 2, 1, 3 is equal to, let's see, minus 11 over 8 times 4, 2, minus 5, plus 1 over 4 times 26 minus 26. So here's one of the vectors written as a linear combination of the other two. Now something that we should notice is this vector isn't special in any way. In this example, and this is usually what happens, if you can write one vector as a linear combination of the others, you can usually write those other vectors as linear combinations as well. So, here we solved for this last vector, but we could have solved for, say, this one over here instead. So that would give us, let's see, 4, 2, minus 5. Well, first we need to move these to the other side, but also we need to multiply by, I'd better do this in 2 steps. I'm going to lose track of something if I don't. So move these to the other side. We get 1 over 4 times 26 minus 26 plus, minus 2, 1, 3. And then we can finish solving by multiplying by 8 over 11. So that's going to give us 4, 2, minus 5. And then on the right-hand side, we're going to get, let's see, simplifying, we get 2 over 11 times 26 minus 26 minus 8 over 11 times minus 2, 1, 3. And, in fact, we could also, if we wanted to, solve this linear dependence relation for this middle vector to get it as a linear combination of the first and the third vectors. So you can see this definition of linear independence really is treating these three vectors equally.